So today, two related things. So the first thing I want to do is go over a little more explicit model of how you solve the aperture problem. And it kind of, I've made sort of, drawings of little, diagrams like a circle with arrows in it. But what is this? Let's just unpack it and actually see all the connections. And I think it helps to sort of see what we would need to do to make a neural network solve the aperture problem. So that's the first half, and then the second half I'll go over this classic paper from 1981 which is the actual paper that kind of defined the aperture problem in the first place. And it's very, it's a mathematical paper. It's very strange looking, but I think it's worthwhile just sort of going through the initial definitions and seeing how it relates to the way that we presented it initially. So starting off with a more explicit model. So what are we modeling? We're modeling, V1. Layer 4B to MT. So MT is where some of the neurons actually can solve the aperture problem and solve the problem that when you just look at a small piece of a contour, you can't pick up the slip. And so you have an ambiguity about what the actual direction is. So the first thing we should do is just say what the actual responses of cells in layer 4B look like. And so this is, if we plot out a graph of how a layer 4B cell responds to direction, so this is the response going this way. You might have something, that looks like a very sharp tuning curve like that. And so this would be like 0 and 360 degrees. But remember, we've got direction and speed. So there's the direction of the vector that we were drawing. So this guy is direction, but we also have the speed. So the speed so here's speed. But you might notice there's a problem now because there's both direction and speed. That's two dimensions. But let's just pick a direction, say, the good direction, and then let's measure how the cell responds when we try different speeds. And so you might find a curve something like that for one direction. But really what we want is we need to know, like, what is the response across all different combinations of directions and speeds. And so this is, a different coordinate system than we were using. We'll put direction here and speed here. So now we got a 2D graph. These are 1D graphs. So you have a 2D graph. And so what does the response of a cell look like? So it might be something. So if we have, let's just label the direction. So here's 0, 90, 180, 270, 360. Okay, so we might have a cell that likes 180. And so, what is 180? That would be like to the left. And if we try different speeds at the same time, we find that it really likes pretty fast speeds. So this is fast and slow. So say we find a cell that likes relatively fast speeds, and if you make the speed wrong, it doesn't respond as well. If you make the direction wrong, it's really sensitive to direction. So it really likes 180, and by the time you get to 90, it's no response. So that's that's what you'd really have to do to characterize a cell. So this is, all combos of direction and speed. And what would another cell look like? Here's another cell that, say, maybe responds to 45 degrees. Put a 45 in there. But slower speeds. And so what you find is all different combinations of cells. And so that's a cell that, it's selective for speed, also selective for direction. So how were we drawing that before? So the way we were drawing that before was we were just drawing it out as a vector. And so what does this cell correspond to? That corresponds to a relatively long arrow. So let me put it down here. So, a relatively long arrow going in the direction 180 degrees. So here's the selectivity of that cell. That would be a thin arrow going in the direction 180 degrees. So that's this guy. And then that's what I was drawing as arrows. That was an abbreviation for here's the response to a whole bunch of different directions and speeds. And so what is this guy at 45 degrees? That guy would be at 45 degrees but smaller speed. So that's an arrow like that. So this guy is that one. So I just unpacked it a little bit. This is what the actual data from a neuron would look like. That was selective for a particular direction and speed. Okay, so then what we said was the way we solve this problem. So what is the initial problem? The initial problem was described as you have a contour, some object here, and the problem is we're looking through a little aperture right there, and we can only detect the perpendicular component of the motion. But the problem is, since we can't detect the one that's sliding along the contour, we don't know what the actual pattern direction is. It could be like that. It might actually be that way, but it could be like this. It's radically ambiguous, much more ambiguous than you would have at first thought. So it could be these two different directions are consistent with that same signal that this neuron would pick up. And so how did we say that we solved that? We said that the way we solve this is if we want to make a detector that detects a particular direction and speed, pattern direction, then what we're going to do is say we want to detect 180 at a relatively fast speed. So that's a thick arrow. And so what we do is we want to wire up a detector that contains all the local directions that are consistent with that pattern direction, and that corresponds to these arrows going out to a circle. And they fall off in length as they become more different in angle. So the idea was we make a whole bunch of detectors like this, all different orientations, all different lengths, and then we find out which one gets the most votes. But what is that sort of in more detail? So let's expand this into actually, what the connections are that would implement this kind of a model. And so we'll start off. So if we go into layer 4B, we find all these different combinations of speeds and directions. So let's start one down here. So this is a little chunk of space in layer 4B. But now we're going to have neurons in here that respond to all different combinations of directions and speeds. So this is direction going in this way and speed going in this way. And each one of those little squares is one neuron. And so you can think of it as like this. It's all the different neurons here that respond to all the different combinations of directions and speeds. And let's say we were doing 180 degrees. And so here's 0 to 360. So 180 degrees is going to be, say we're doing a relatively fast speed at 180 degrees. So what is that going to correspond to? Well, it's going to correspond to a unit, say, a unit somewhere here at 180. So that's 180 right there. And now what we want to do is draw this diagram out here explicitly across all the units. And so what's going to happen is as we move off to the side, the responses are going to respond to lower speeds. That's what this diagram implies. So if we happen to have a contour that's actually at the same, that's moving perpendicular to the contour, that will give us the maximum speed. And then as we move off to the side, the speed goes down. And so it's going to basically cover like a half of a sine wave across that graph of direction and speed. And those are going to be all the possible directions and speeds that could signal this one. This is, detector for this pattern motion. Okay, so now we already knew that if you just have one detector, it's hopeless because you can't tell, you can't tell what the actual direction and speed is. And let's draw out this problem over here. I'll draw out this problem in a different coordinate system. So let's draw out that problem just in our Cartesian speed direction coordinate system. So what does this problem actually look like? And this is what we're diagramming over here. So what the problem looks like is if we have, say, a signal that comes in at 180 degrees and relatively fast, it's possible that that's actually the pattern direction. And here's all the different possible combinations of directions and speeds that are consistent with this pattern direction. And that's basically what we're drawing here. But now let's consider there's another family of directions and speeds that indicates this pattern direction. It's a faster pattern direction. And if we've only got one sample, if we only have that sample, then it's possible that the pattern direction could have been off to the side faster. That's this diagram here. But it's also possible it could have been, off to this side, something like this. So it could have indicated that pattern direction and speed. And so there's a whole bunch of different possible pattern directions. That's exactly what we're drawing here, that a single sample of direction and speed from one of these Reichardt detectors is consistent with. Now, all you have to do to solve the problem is get another sample. So if we got just one sample here, all these different possible curves intersecting it are a possible pattern direction. But if we get another sample, say we get another sample over here, even two samples will eliminate these other curves. So we can see that it can't be that guy, and it can't be that guy. So just with a second sample. So which has to come from note a different part of space. So basically here's our, second sample disambiguates. Disambiguates. So here's our first sample. So if we just have one sample, like this case, there's a whole bunch of different direction and speeds of the pattern direction that are possible. But as we build up more samples, then we can disambiguate the problem. And so that's going to require multiple samples across space. And so if we imagine we've got one MT unit up here, so this is our MT, and this guy is V1 layer 4B. So we're going to connect all of these guys up to that, so all these guys go up there and connect up to this MT unit at this location in space. Because all of those are the local directions that are consistent with this, with that center pattern direction. But if we just have one sample from one point in space, can't solve the problem. That's this situation. So now we have to expand our model in order to include other points in space. So here, let's sort of go off in this direction, and we go off in this direction, off in this direction. So we'll expand our model to include more points in space. Oops. So basically what we're saying is at each point in space, we have all these speeds and directions. And it's kind of like orientation columns, except these are direction and speed columns. So the same way where orientation columns, at one point in space we have all different orientations. You go to another point in space, all different orientations. Same thing going on here. So one point in space we have a bunch of speeds and directions. Another point in space, we've got a bunch of speeds and directions. Same thing going on over here. So basically, this is like the x direction in space, and here's the y direction in space. So each one of these little things are two different little pieces of space. So now what do we have to do? Well, we've got to go to all those other places in space and hook all those guys up too. So we're going to have to sort of pick out the set of directions and speeds, the same ones that we have there. Something like that. And then connect all those guys up. And so all of those guys have to connect up. So you can see we're ending up with a lot of wires. Okay, all those guys connect up. And then do the same thing, over here. So here's all the ones that connect up there, and do the same thing. So you have to do this whole thing across space. Because at each point in space, we just have one sample. And one sample is not enough to figure out, which of these guys is the correct one. And so So what does that look like in real life? You'll get multiple samples. So say this point in space got that local direction, and this point in space got that local direction, and this point in space got that local direction. So there'll be a whole bunch of different, depending on what the contour is at each point, there'll be a whole bunch of samples. So this is, one sample. So one local direction sample from one Reichart detector. And so the way we solve this problem is we just look across space and then find out, which one of these collections of local directions and speeds gets the most votes. So I just drew one of these guys. So this is just this horizontal one, horizontal relatively fast. And so you're going to have a whole bunch of other units up here with a million connections coming up to them. There's a whole bunch of connections coming up to them that come from, that are set up to detect different directions, et cetera. So there's going to be another, let's just draw one other one. So say we have a slower speed. So here's another set of units that are going to project up to a different MT unit. Might be something like that. And so all those units across space again are going to go to this guy. And so you can see it's a rat's nest of connections, but it also makes the point that when we look at a layer 4B neuron, if we test for direction, we get a sharp tuning curve, something like that. And so when you first look at that, you say, layer 4B is really good. It has very sharp tuning curves. If you go to MT, what do you find? Well, the tuning curve is kind of more sloppy. It extends, if this is 0 and 360, it looks like layer 4B is very selective for direction. Look at MT, it doesn't look very selective for direction. But that makes sense from this point of view, because if you look at this MT unit here, so let me put this is our MT. This is, V1 layer 4B down here. If you look at that MT unit, it's getting input from a whole bunch of different directions. This is direction, remember, and there's speed. And so it's getting input from a whole bunch of different directions over 180 degrees. That's what this picture is over here. It's all these different directions that are providing input to a single MT unit. And so you'd expect it if you just test it with a very simple pattern, just like a bar, which is what this graph comes from. If you just move a bar perpendicular to its edge, it looks kind of lazy. Why is that? Because it's getting all these different directions as input. But it's smarter than it looks, because it's got this specific set of inputs that are designed to detect different pattern directions. So the other one I drew here, so I drew this second one here. Let me just draw that one out in this diagram. So that one would be a slower speed, and that slower speed would be about 90 degrees. So that means it would be so say we wanted to detect this pattern direction, then we're going to need, this local direction, or that local direction, or that local direction, and that local direction. And so that corresponds to this guy. So So that guy, that corresponds to this guy, whereas this guy corresponds to that guy. So that's the actual sort of like full metal jacket picture of what's going on. So what you're seeing is you're seeing that you've got to connect up a bunch of different directions, and speed combinations. There has to be the right speed and the right direction, but expanding over a number of different directions. And then you've got to do the same thing across space in order to be able to solve this problem, because one detector is only going to detect one little edge. And so if you want to solve the problem, you have to have another detector over here that's detecting something coming off of that edge. And so that's how you actually implement it. So many different parts of V1 layer 4B that are from different parts of the map, the X, Y map here, connect up to one MT neuron in order to solve this problem. Okay, so hopefully that kind of unpacked what these diagrams actually mean in a little more explicit. So it's a particular combination of connections from particular combinations of direction and speed, and that all go to one unit, and then that same thing happens across space so that we can solve the problem. Okay, so any questions about the sort of unpacking this diagram, what this diagram actually means? So this is, how to solve the aperture problem. Yeah.
So this is how neurons react when what?
So the idea is we don't know that these are the exact connections, but this is one possible explanation for why the neurons in MT are capable, of responding correctly if you give them something like this. So if you give a neuron in MT something like that, and you move it up, it will actually respond. Whereas if you give a neuron in layer 4B something like that, it doesn't like it. And in fact, so if you give a neuron in 4B that likes up, something like this, it doesn't like it. So here's the contrast. So we give the neuron just a bar like that, and we find that MT, that layer 4B will respond to up if you move a bar up. If you move a little plaid pattern like that up, layer 4B doesn't like it. And in fact, layer 4B will prefer a plaid pattern moving off to the side. So if we do that, then layer 4B will like it. And the reason is because now layer 4B is seeing motion perpendicular to the contours. And so what we're trying to explain is, why does layer 4B get confused by this, but MT doesn't? So if you test in MT and find a neuron that likes a bar moving up, it will also like this plaid pattern moving up. And so it's solved this problem of how to combine all this local information across space. So what this is a possible explanation for how MT might solve this problem. Nobody has worked out all the detailed connections, but it's a possible explanation for how come MT can actually detect that the pattern is going up when it's getting input from layer 4B and V1 that cannot solve this problem, that's confused and only detects perpendicular motion. Yeah, so you can think of it as it's a neural model that's a possible explanation for how MT might be doing this. Okay, so now we'll inadvisedly quickly go over Horn and Schunck. And I put the paper in the readings if you want to look at it. If you try to read it, you probably won't get very far because there's a bunch of math in it. But I thought it was worthwhile putting it in there because it was yet another way of defining the aperture problem. And it was actually the first way that the aperture problem was defined. And one good practice, just from the point of view of learning how to read scientific papers, is this is how the problem was initially defined. And so you had to, this is the only way that you could get the problem. And so it's sometimes worthwhile to sort of look at these original papers, even though they're hard to read, because what you want to do is read a current paper that might be hard to read, that's now sort of like pushing the boundaries. So this is from 1981. If you've ever used an optical mouse, like that has a little light on it and you move it over something, this algorithm is built into the optical mouse. That's how the optical mouse figures out, what direction. So it's current technology. We're 20, 30 years old now. So how did this paper start off? So it started off, so we make the assume objects don't change brightness. So is that a good assumption? Of course not. Objects change brightness all the time. If you move an object around, objects when they move. So not a good assumption. You might move an object into a shadow, maybe, or move it into the sunlight, or move it next to a light. Obviously, objects are changing brightness all the time. But to a first approximation, if we don't move something a lot, we can say, let's just assume that in general the brightness doesn't change. So that's our first assumption. And then we can do some math. And so how do we translate that into math? We translate it into math as, so E is the brightness. The derivative of the brightness just means the change in brightness. So the change in brightness with respect to time, so that means the change in brightness over a small time equals 0. And if you're ever doing math, I look at this equation, I go like, boy, that equation just doesn't do anything for me. It's like, something equals 0. What can I do with 0? It's kind of, so now let's define what the brightness is. So the brightness is a function of where you are in x and y in the object, and then what time we're at. So that's the thing that the derivative of which is equal to 0. So how do we expand this? So we'll just put it off to the side. So first we have a movement, and so we have to say our brightness doesn't change if we do a small movement. And so here's a small movement. Add a little bit of x, add a little bit of y, add a little bit of t. So that's a small movement. And then here's our assumption. Assume that it doesn't change. So here was like a previous point in time and space. Here's a new point in time and space. And they're supposed to be the same because we assume it didn't change brightness. Okay, so then expand as Taylor series we'll just leave that out. So we can sort of approximate this by taking derivatives of it, whatever. And then we've got some chain rule in there. We'll just leave that out. Simplify. And so what do we get after we do all that? You can go in the paper and just look at it. So we get another equation that equals 0. And so that's our critical equation. And so what that equation says is the partial derivative of the brightness with respect to the x direction. So what does that partial derivative mean? That means let's ignore how things are changing in the y direction or how things are changing at time and just consider how the brightness changes when we move in the x direction. So we go a small distance in the x direction and see how the brightness changes. And then that's multiplied by the actual velocity in the x direction. So what is that? So that is, say here's the velocity. So we could decompose that into an x and a y part. And so here's the x part. So that's the, that's the change as we move in the x direction, and here's the y part. So we've decomposed that velocity into an x and a y part. So this is just the x part of it. So this says you multiply the velocity, whatever it is going in the x direction, the x direction part of it, times how the object changed in space. So that's the meaning of that. And so let's finish up our equation. So then we got a similar one. We look at how the object at a point changes in the y direction, and we multiply that by the y velocity. And then we finally just add how the object changes to the next time point, and that equals 0. So that's our equation. That's our starting equation for the gradient model. And so now we want to do is solve this equation to try to figure out what the velocity is, because that's what we want to know, is what is the velocity. And so when we look at this, there's an immediate problem. So we've got this, which is something we can figure out from the image at a point, and this, so that's just how does the image change when you move small distances in x and y, and then this is how did the image change at a point when we looked at the next time point. So these are all data, so that's good. But the problem is we've got 2 unknowns. So we can't solve this. 2 unknowns. So that means the equation is underdetermined. We've got like the x and the y direction, so we can't solve for it. And so how do we deal with this? Well, let's just solve for just the y component. So this is the way the aperture problem, believe it or not, was originally stated. So let's just solve for the y component. So just take this equation and just fish out the y component. So here's the y component, and that equals partial derivative of this guy with respect to x times dx dt, a minus there, divided by this thing in the y direction. And then we're subtracting off. It's a big mess, but let's just write it out. So how does the image change over time, divided by how does the image change in the y direction. Okay, so that looks like a mess. So this guy's the unknown. That's the second unknown. So what is, if we simplify that equation down, what is it? It's a graph of a line. So you can sort of think of this as y equals slope times a variable, plus the intercept. So this guy. So what is the slope? So the slope is this guy. That guy's the variable. And that's the y. And here's the intercept. So the intercept we can figure out because that's all from our data. That's all from our data. The slope we can figure out. The m we can figure out because that's all our data. And so the only thing left is we don't know what the x is. And so if you plot out that line, so let's just plot out that line. Plot line for dy dt. So plot out that line. So what does it look like? So say we'll get some line like this. So there's a line, and so what's what space are we plotting it in? So we're plotting it in the space in this space here. So this is the y velocity in that direction, and this is the x velocity in this direction. So this is velocity space. That we were already using velocity space whenever we just made a bunch of arrows. That was just another way of representing velocity space. And so what does that line correspond to? That corresponds to all the possible solutions. And so what are all those possible solutions? They're just velocities that are along that line. So points along that line just indicate velocities. Points along this line right here, defined by that equation. So these are just velocities, and that's what we always were drawing from the very beginning. So this is the original statement of the aperture problem, which is if we plot a line, because we've got this second unknown, so here's the first unknown. So if we plot a line for the first unknown, we've got this ambiguity, and this is the original definition of the aperture problem. All those possible directions are possible directions given the data. So given the data, and so you might wonder, like, how does this fit into a Reichardt detector? Well, if you look at what our data is, so what is our data? Our data is a little offset in the x direction and the y direction, also known as the Reichardt detector. That's basically what the Reichardt detector was. Remember, it's got a little offset in the x direction, in some direction like that. It's got a little offset in time, and we're adding it together. That's our Reichardt detector. And so this is basically a Reichardt detector. It says, the data from this detector is, let's move a little bit in the x direction and see how it changes. That's this change in x. Let's move a little bit in the y direction. We have to sort of do 2 dimensions, but basically we got 2 dimensions. And then let's just see how it changes over time. That's this delay here. So it's basically like a Reichardt detector with really tiny, just going to the next pixel. And so when you plot the line, what we find is we have this possible pattern directions. All of those are possible. And so how do we solve this problem? So if you read in the paper, we add what's called a smoothness constraint. And so what we do is we find the solution that is the smoothest solution. And what does that mean? It means like where the solution velocity changes nice and smoothly like that. Now you might wonder, what does that correspond to in the first model? And so what this corresponds to is, MT receptive fields are bigger, are larger. That's what the smoothness constraint corresponds to. We look across space. So how did they solve this problem? So for a given point, it's ambiguous. So how do we solve the problem? Look across space. Make a bigger receptive field. So that's basically completely different statement of the problem, confusingly different statement of the problem, but basically same problem. We've got this ambiguity. So let's just work out in the last 2 minutes, just work out one simple example. So imagine we've got, to make it really concrete, so imagine we've got 2 time points like this, and we've got a single pixel like this, and let's say the single pixel moves just 1 pixel over. So let's just run this equation to show that this equation isn't so scary as it looks. So how do we run that equation? We first say, how does this image change when we move in the x direction? And so how does that image change? Well, it's sort of got, dE, sorry, partial E dx got darker, okay? And then we see how that's this term here. So now we say, how does it change in the y direction? So that this is the partial derivative in the y direction. It also got darker. Okay, then finally we have to get this data point. How did it change over time? So let's see, how does this guy, how does this guy change over time? This guy there. So that's the change in the brightness over time. And so what happened to that one? It got brighter, +1. Okay, so that's our data. And now we're going to propose a direction that we moved. So let's say we moved just in the x direction. So what is that? Well, that's the x direction over time. We moved in the x direction, and the y direction over time, we didn't move at all. Okay. So when you run this equation, what's going to happen? It's going to be true. So the x direction is 1, and the y direction, so the y direction, we didn't move in the y direction, it also will zero out this term. And then when we look at the brightness term, it's going to basically equal +1. And so when we take the x component here of the velocity, multiply it by this guy, we get -1. When we add them together, we get 0. So the y component will zero out this term. And so we'll just have, so if you look at that, so that's true, just at the level of 1 pixel. But what is the aperture problem? The aperture problem is, well, what if instead of doing that, what if instead of moving to the right, let's say we moved up. So what if we moved up instead of moving to the right? Here's where we were before. So here's where we were before. So in this case, we moved 1 pixel to the right. In this case, we moved 1 pixel up. I won't write it on here, but if you do that same calculation of looking at how the image changes in the x direction, how the image changes in the y direction, how the image pixel changes over time, you'll find that works too. And so there's your problem. That's your aperture problem. Either of those will satisfy this equation based on the fact that you're assuming that the brightness doesn't change when an object moves. Okay, so strange, doesn't look at all like the original aperture problem, but this is how it was originally defined. And where did this come from? They basically, it was at MIT. They had like a bunch of Defense Department money. They were trying to sort of figure out what direction missiles are going. They got video, and they just took in some video frames, and then they just tried to process it, and they said, we can't actually tell what direction things are going. That's literally how it was discovered. And so then they had to figure out something that would get around the problem, and that problem was the smoothness constraint, also known as looking across space, larger empty receptive fields, and that allows you to basically solve the problem. Okay, Stan, I think we'll just under the wire. Stop the recording there.